So we're going to talk about combinatorics a little bit today. In particular, we're going to build up to what's called the counting principle. So combinatorics is literally just the study of counting. And some basic terminology that we're going to kind of need to know a little bit in this chapter is experiment. So an experiment is an activity with an observable outcome. So an example of an experiment might be you flip a coin 3 times, right? And then the outcome might be heads, heads, tails or something, or the outcome might be tails, heads, tails. There's a bunch of different possible outcomes here, and the set of all possible outcomes of an experiment is called the sample space of the experiment. Okay, so like the heads, tails, tails, heads, tails, tails, and heads, heads, tails, those would be elements of your sample space. An event is just one or more of the possible outcomes of an event. So one event could be that the first 2 coin flips are heads, or maybe if your experiment is drawing a hand of 5 cards from a 52 card deck, one event could be that you draw at least 2 spades or something like that. So back to like that flipping a coin example, because it's very basic. Let's just list the elements of the sample space defined by just the experiment of tossing 2 coins. So you could just list them all out as a set. So we'll just like say like HH to denote that you flip heads twice in a row. HT means you flipped heads and then you flip tails, which is different from flipping tails first and then heads, and then tails, tails would be the last one. And those are your only 4 possibilities here. You could instead list these using a table. Obviously, this is not like that useful in this in this particular experiment, but listing things out in a table does actually end up, how do I say, making things like a lot more visually appealing, or like aesthetically like easier to like read what's going on in the sample space when you have multiple like possible like outcomes for your event. So maybe like if your thing is rolling a 10-sided die, then you might have like the numbers 1 through 10 for the first for that first row, and then 1 to 10 for like that column, and then you would have like in your table 1 1, and then like 1 2 and 1 3 and 1 4 1 5 up through like 1 9. And if it's a 10-sided die, then be like 1 10 after that, or maybe it's like a 0, so like 1 0 might have gone at the start, whatever. But that would be like a lot harder to like list out just as a set. It would be probably better to write it using a table. And even in this like 2x2 example, like this still is like a little bit more useful than this. So what events could we consider? We kind of already talked about this. Like you could consider the event of just like, you get at least 1 heads and at least 1 tails. That would account for like these two possible outcomes. Okay. So what if we instead flipped 3 or 4 coins? So if we wanted to list out all of the events in the sample space, or all the outcomes in the sample space, we could, we could also like maybe try to list out what goes on in a table, but like the table, because there's like 3 stages for what happens, like the table would have to be like 3-dimensional. And then if you flip like 4 coins, then like that table would be like even more complicated. And I don't even know how it would kind of work out. So what we could do instead though is use a tree diagram. And so the tree diagram is going to look like this. So you could start, it doesn't really matter how you orient the tree. So you start, nothing has happened yet. So at this part of the tree, nothing has happened. And then either you flip heads or you flip tails. And then from there, you could flip again. You could either flip heads or you could flip tails. So here's heads, here's tails. And then just copy and paste because the same thing can happen down here. After you flip heads, then you could do heads or tails. And then same over here. After you flipped heads twice, you could flip either heads or tails. And then, oh, that is not the right thing to copy and paste. Okay, it's about to get a little bit messy, but okay, I'm just gonna, yeah, copy and paste is like gonna kind of stop working here. So I'm just gonna fill it in. Nope. Well, hopefully you kind of get the idea that like this sort of just keeps branching off into just like all these possibilities. Okay, I'm gonna shorten that a little bit. I can look like this. Heads, tails, heads, tails, heads, tails, heads, tails. Okay, cool. And so now over on the bottom, we could list, or over on like the right end of the tree, like once we reach like the end of it, like we could start just listing out what outcome we had. So over here, you can kind of tell that this was like heads, 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 just to get to that part on the tree. Or you could do heads, heads, tails. You could list that out here, and then this would be heads, tails, tails. Sorry, heads, tails, heads, heads, tails, 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 heads, heads, and so on. Okay. Cool. All right, so tree diagrams can be sometimes helpful for observing specific events. So relating this to like the previous example, like if I kind of listed it like this, I could say what outcomes would happen in the event of like you flip heads first. So you can kind of just say like, oh, well, if I do heads first, then it's just going to be anything on this side of the tree, and then just sort of observe from there. Or you might say, what about if you do heads at least twice? So you can just kind of just go to this table and just find all of the places where you do heads at least twice, and it would be those four right there. And yeah, maybe they're not like going to be super well organized in this table, like as much as it was for like, oh, you do heads first, but that's fine. You can still just kind of look and see what's going on. All right. Okay, so here's another example of this. So 4 cards are labeled A, B, C, and D, and there are 4 boxes labeled A, B, C, and D. Okay, so you have 4 cards. Boop, 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 boop. These are labeled. And then you have 4 boxes. Come on. So the boxes are different. But then the boxes themselves are also labeled. Okay. All right, and then you just want to, arrange these cards to go inside of the boxes, and so on, right? So let's say that we want to just know how many elements are going to be in the event that the letter D is in the box labeled A. So we're going to take this card D and then put it in the A box, and then we don't really care what happens to these ones over here. Okay, so what I'm about to show you, I'm going to like preface this by saying that there are better ways to do this problem that we will do later, but there's a homework problem in the section that I don't really think that the homework problem belongs in this section, and so what I'm going to kind of tell you is just it's a hard problem, but what I'm going to tell you can maybe sort of help you be able to do it without me like giving it away. So, okay, so here's our tree diagram. So, so we're gonna start up here. So I'm orienting it like vertically just so I have like enough space for like what's going on. And then you can kind of list things out like so. So you can say like, all right, well, what's gonna go in box A? In box A, you could either have A, B, C, or D. And I'm ignoring the fact that like we're putting D into the box labeled A just because you're gonna probably need to know like this whole thing for like when you get to that homework problem. Okay, so yeah, in box A, you have like 4 options, right? And then what happens in box B? Well, let's go to this part of the tree. Let's say that we do A first. Then what can go in box B? Well, we already used A, so A cannot itself go in box B, right? Because we've already used it. So there's only 3 options left. There's B, C, or D. So B, C, or D could go into box B. Well, what if like what if B goes into box B and A goes into box A? Well, then box C could either be C or D. And let's say that we put C in there. Well, then what could go in box D? Well, I've used the other 3 cards, so there's only one option left at that point, which is D. And so we would say that like A, B, C, D are like the order of the cards that went into the box. Similarly, you could say card C goes into box A, and then card B goes into box B, and then D goes into box C, and then A goes into box D. So just sort of following down this part over here. Okay, let's like just fill in this last part of the table just so we're kind of all on the same page for what's going on here. So if I were to do B goes in box A, what are my 3 other possibilities for box B? Well, we've already used B, so A, C, and D are the only ones left. What if we use B then A? Well, then C and D are the only possible options left. If C goes into box C, the D has to go into box D. If D goes into box C, then C has to go into box D, right? So these 2 rows are kind of just like reversed from each other. All right, what if we do D then C, or sorry, B then C? Then we haven't used A or D yet. So we would have those options, and then we just sort of flip it for like A and D could go into box C or D, and then we just sort of do it like that. And then last one, B then D, then you could either do A or C left for box C, and then depending on which one you do for box C, you put the other one into box D. Okay, maybe I won't do all of this part right here, but let's make this a little smaller. And yeah, so if we were to do B, then A, then C, then D, we do B, A, C, D, or we could do B, A, D, C, or B, C, A, D, B, C, D, A, yes, so on. Okay, moving on. So let's get to the counting principle now. Oh, wait. No, sorry, I wanted to tell you one more thing before I get to this. All right, let me just finish this. So B, D, A, C, B, D, C, A, just because I can. Okay. So we didn't say this. So count the number of elements in the event that the letter D is in the box labeled A. So that would say we just go to this part of the tree and then we just count. Well, these would be all of our possible outcomes. So we can just say, all right, well, there's just going to be 6 possible outcomes. All right, this is like a pretty simple event. You could have like more complicated events like let's see, what would be slightly more complicated here? You could say the event that B goes into box C. So that would be like a little bit harder to observe here. But if you need B to go into box C, then we just kind of look for all of the places where B shows up right here. So that would be right here, that'd be right here, that'd be right here, 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 and here. So it looked like that there are 6 possible options right there. So depending on what your event is, if you have this tree, then you could just kind of like look at it visually and try to figure out like what's going on with based off of that. Okay, anyway. So counting principle. So using the tree diagram, we can kind of see that like we can count possibilities just using multiplication. So the event where like D went into the first box. So this was like, oh, we go D first, and then like it'll be anything that happens after that point on. So then there were like 6 of them, right? So if we wanted to like count like those 6 right there, well, there were 3 possibilities for the second box, and then there were 2 possibilities for the third box, and then the last box, there was only 1 possibility left because all the other cards had been chosen, right? So we ended up having 3 times 2 times 1 total possibilities. 3 times 2 times 1, that's 6, right? And you could just count how many possibilities there are for like the entire sample space by counting it like, okay, well, you have 4 options for the first box, and then 3 options for the second box, 2 for the third, and then 1 for the last one. So there were 4 times 3 times 2 times 1, which is equal to 24 total possibilities here. And so this is an example of what's called the counting principle, which says that for a multi-stage experiment E, where N1, N2, N3, and so on are the number of possible outcomes for all the stages of E, then you could just multiply all of these numbers together to get the total number of possible outcomes for your event. So over here, N1 would be 4 because there are 4 possible options for the first stage, which is, choosing a card for the first box, and then choosing a card for the second box. That's stage 2 of the experiment. There are 3 options. N sub 3 is, well, there are 2 options for the third stage of our experiment, which is choosing a card for the third box. And then N4, how many options are there to choose a card for the fourth box? Well, all the other 3 cards have been used at this point, so there's only 1 possibility. And so the total number of outcomes is just N4 times N3 times N2 times N1, which is literally just equal to this. Okay. Yeah. All right. So let's apply this. Let's say that we roll a 6-sided die, then we flip a coin, and then we draw a card from a deck of 10 cards. How many possible outcomes are there? Well, there are 3 stages in this experiment. Number of possible outcomes for the first stage. Well, we're rolling a 6-sided die, so there are 6 possible outcomes here. How many options are there for the second stage of our experiment? Well, we're flipping a coin now, so it's either going to be heads or tails, so there are 2 options. And 3, how many options are there for drawing a card from a deck of 10 cards? There's 10 options. So we do 6 times 2 times 10, which is this 12 times 10, or 120 possible outcomes. Okay, and you don't have to do like a tree diagram. You don't have to like make a table. You don't have to list things out. Like you could literally just say, well, there are this many possibilities here, here, and here, and then just multiply them together. Okay, let's do something slightly different. So let's suppose that we have a class of 12 students and we want to know who the 3 tallest students are. How many possible outcomes are there? So if you have 12 students, let's just label the students like student 1 through student 12, I guess. So your top 3 tallest students might be like student 5, and then student 7, and then student 3, right? So how many options are there for who the first tallest student is? Well, there are 12 students, so there would be 12, right? Okay, well, once we've decided who the tallest student is, so like N1, we're like choosing like we're choosing who's the tallest. That's like the first stage of our experiment. Second stage of the experiment is deciding who is the second tallest. Well, if we've already decided that student 5 is the tallest, Jimmy's the tallest, then there's only 11 other students left who could be the second tallest, right? So N2, it would be incorrect to say that there are 12 options for who is the second tallest student, even though technically it is possible for, there are 12 possible students who could be the tallest, second tallest here. But in this experiment, we've like implicitly already decided who is the tallest. So if we already know Jimmy's the tallest, then there's only 11 possible options for who's second tallest. And then if we know who the first two tallest people are, then how many students could be the third tallest? Well, we've eliminated 2 options, so there are only 10 possible options for who the third tallest is at this point. All right, so how many possible outcomes are there? So number of possible outcomes. This is going to be equal to 12 times 11 times 10. 12 times 11 is 132. 132 times 10 is 1,320. We just tack on a 0. So that's how many outcomes there are. Notice that we don't really care at all who's going to be fourth or fifth tallest or anything like that. All we really care about is like the first 3 tallest. This will come up again later. All right. Suppose that all right. Yeah. So this one is like all about counting with or without replacement. So like in the previous one, like this was technically like a without replacement style problem where once you've decided who's the tallest person, that tallest person can't be reused as like the second tallest or the third tallest person. They're out of the running for who is second or third tallest. We're not replacing them back into the problem. So here's a better example of this probably. So let's suppose that we draw 3 cards from a deck. Deck has 52 cards. How many possible outcomes are there if option 1, we replace the card after every draw, or option 2, we do not replace the card after every draw? So if you're just playing, pick a card with your friend and they give you a deck of 52 cards, you draw a card and then what are the odds that it's an ace of spades? Well, it's like 1 in 52. Like there's 52 possible options. And then if you want to like keep guessing, you could either like keep that out of the deck, or you could put that back into the deck and then like repeat. So if we put it back into the deck, then we're replacing. So we're drawing 3 cards from the deck. So for number 1, we have 52 options for the first card. And then if we put it back, then it's possible to draw that card a second time. So there are 52 possible options for the second draw as well. And then the third draw, we put whatever that card is back again. And so we could just keep drawing that same card every single time. And so it's just 52 times 52 times 52 possibilities for this situation. If we're not replacing the card after every draw, maybe like you're playing a card game and like you need to draw like a hand of 3 cards, right? So in this case, like you don't put the card back, you're keeping the cards out of the deck. So you have 52 options for the first one. And then after you've drawn that first one, there's 1 less card in the deck. So there's 51 possible options and then 50 options for the third one. All right, just because you keep removing cards and you're not putting them back. So putting them back would be this. Not putting them back would be this. All right, so maybe you can see if you can figure out this one. How many ways are there to create a 5-letter password if we are not allowed to reuse letters, or if we are allowed to reuse letters? Okay, so you can assume that these passwords don't include like any special characters or symbols or numbers or anything like that. Like it's just the letters like A through Z. So how many 5-letter that should just say 5-letter passwords. So how many 5-letter passwords are there under these two possibilities? So pause, give it a shot, come back. All right, so option 1, if we're not allowed to reuse letters, so then there are 26 possible options for the first letter of your password, 25 possible options for the second, because you've already used up the first letter, and then there are only 25 left after that. Then 24 possibilities after that, 23 after that, and then 22 after that. And then this would count for 1, 2, 3, 4, 5 choices of a letter. And so whatever this product is equal to would be the total number of ways there are to create a 5-letter password that does not reuse letters. Option 2, if we are allowed to reuse letters, there are 26 possible options for the first one, 26 for the second one, 26 for the third one, fourth one, and fifth one, and so on. So you could just, of course, write this as 26 to the fifth, and whatever that number is equal to, that's your answer here. All right, and so yeah, that's it. I hope this helped, and see you in the next one.